So in this lesson, we'll do more interpreting graphs, but now we'll be looking at graphs that are not linear. In the previous lesson, all the graphs were linear functions, straight lines. So the idea is still the same, where we have the two variables, the vertical and the horizontal, and we just want to see how they relate to each other, and we can pull information from the graph. Okay? So example 1, a person is riding on a Ferris wheel. The height of the person off the ground changes as they travel around the wheel. The relationship between this height and time is shown on the graph. So vertically, we have one variable as our height in meters. So this shows us as the person is taken up on the Ferris wheel, they come up to the top. And then we all know a Ferris wheel goes round and round. So once they reach the top, then their height starts coming down again. And then along the bottom is our time in seconds. Okay, so question 1, what is the maximum height reached by the person on the Ferris wheel? Well, if we look at the graph, the maximum height, the highest point that this person ever reaches is 7 meters, okay? So 7 meters. Then B, what is the boarding height for the Ferris wheel? Well, typically people get on the Ferris wheel not right at ground level because the Ferris wheel would get stuck. So there's a platform usually, and we see that the lowest height that anyone ever reaches is 1 meter, right? So we can assume that this is where they get on the Ferris wheel, because then immediately afterwards their height goes up, okay? So B, their boarding height would be 1 meter. Okay. C, approximately how high is the person off the ground at t equals 5 seconds? So at 5 seconds, if we look over here, so we don't have 5 exactly, we have 4 and 8. So that means halfway in between 4 and 8 would be 6, would be about here. Halfway between 4 and 6 would be 5, so that'd be about here. And then if we bring that straight up, we see that at about 5 seconds, the height, the graph touches right here. So that's about 6 meters. So at 5 seconds, we can say that the height is, the person is 6 meters off the ground. Now D, at what times is the person 1 meter off the ground? So again, we can circle all those at 1 meter there, 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 and there. So then we can just look down at our graph, 24 seconds, 16 seconds, 8 seconds, and 0 seconds. So we can say at t equals 0, t equals 8, t equals 16, and t equals 24. The height, the person will be 1 meter off the ground. Okay, example 2, a bacteria population is growing in a petri dish. The concentration of bacteria per square centimeter is on the vertical axis, and the time in hours is on the horizontal axis. So again, the concentration of bacteria per square centimeter, and the time in hours goes across the horizontal. So the first question, A, determine the time when the concentration was 120 bacteria per square centimeter. So this is our concentration, so we go up to 120 and then go over, and it hits the graph about here. So then we look down, and the time was 4 hours. B, approximate the initial concentration of the bacteria. So the initial would be at time 0, so this is where we start from. And if we go up and look, so it's not exactly like it's not on, but we can approximate and say that that looks about halfway between 40 and 20, which would mean 30. So we can say approximately 30 would be the initial concentration of the bacteria. Okay, approximate the bacteria concentration at t equals 5 hours. Okay, so if we go to our time in hours 5 and go up until we hit the line. Okay, so now this looks like it's a little bit lower than 180. So it's a little bit lower than 180, but it seems like it's a little more than halfway. So probably a good guess would to say at 5 hours, the bacteria concentration is 175. Okay, D, how long does it take for the population of bacteria to double in size? Okay, so this is a little bit trickier. So we have to look, looking at the starting point, we said that was approximately 30. So we want to know how long does it take if the population size is 30 and it doubles, that means it's going to go up to 60. So we want to look at the graph where it hits 60. And if we look at the graph, it hits 60 after 2 hours. So it goes from 30 and doubles up to 60 within 2 hours. And then we can check that again. So if it's at 60 at 2 hours, then we want to check when it doubles, it'll be at 120. So we go up to 120, and the time is 4 hours. So from 2 to 4 hours, it doubled again. So then we can say it takes approximately 2 hours for the bacteria to double. Okay. Now, E says predict the bacteria concentration at T equals 8 hours. Well, that would be easy if it was on the graph. We could just read it off the graph, but that's not there. But going back to our previous answer, we said the population size doubles every 2 hours. So if we just look at the population at 6, so at 6 there was 240 bacteria. So in 2 more hours, that would be 8 hours, it'll double. So 240 times 2 gives us 480. So we can say at 8 hours, the bacteria population, we would expect it to be 480. Okay, so example 3, a soccer ball is kicked from ground level. Its flight path is shown on the graph. The height of the ball in meters is on the vertical axis. So we have the height here. And the distance the ball travels horizontally is on the horizontal axis. So this is like how far it travels. So if you want to picture someone is kicking the soccer ball, and they kick it up into the air, and then it comes down and lands over here. That's probably the best way to visualize this. Okay, so question A, what is the maximum height reached by the ball? Well, if we look, the top of that, of the graph never goes above this line at 4, so we can say that the maximum height is 4 meters. And it's important to put your units in whenever you're dealing with this. So if that was 4 feet, you would put 4 feet, but it's meters, so we put meters. Okay, B, how far does the ball travel horizontally when it reaches its maximum height? So it's asking, like, when the ball gets up to this point, to its highest point, how far has it traveled this way, horizontally? So we go up to the maximum height, and that's at 4 meters right there, and then we come down and look and see that it's traveled 6 meters horizontally. That's the point where it reaches its maximum height. So we can say 6 meters. Okay, C. Whoops. What's the initial height of the soccer ball? Well, we'll just look here. The initial height, the ball hasn't moved. So when the ball hasn't moved, that's its initial position. And when it hasn't moved and it's at zero horizontally, it's also at 0 vertically. So the initial height of the soccer ball is right here at 0. So we can say 0 meters is the initial height. D. How far will the ball travel horizontally before it hits the ground? So the guy kicks the ball, it goes up in the air, and then it comes back and hits the ground here. So that means that it's traveled 12 meters before it hits the ground. Approximate the height of the ball after it's traveled 2 meters horizontally. So we go over to, it's traveled 2 meters horizontally. Now we go up to see the graph, and that would be 2. It's slightly above 2, but it's not quite halfway there. So this you really kind of have to eyeball, and you could say 2.2 meters approximately, but probably 2.3 would be okay as well. And F, determine the horizontal distances that correspond to a height of 3 meters. So a height of 3 meters, so we need to look at height of 3 meters, and then we've got 1 point there, but then the ball also comes up, it hits 3 meters here, then it goes above 3 meters and comes back down to a height of 3 meters again. So there's 2 spots that we have to be aware of, okay? So, and if we just draw our line down, that gives us 9 meters and 3 meters, okay? So the ball has a height of 3 meters at 3 meters horizontally and 9 meters horizontally. Okay, example 4. Hiroshi's son is operating a remote control truck in front of a motion detector. His son is merely driving towards or away from the detector. He's not moving the truck from left to right or vice versa. The motion detector records the distance between itself and the truck at regular time intervals. The resulting graph shows the relationship between this distance and time. So, question A, how far is the truck initially away from the motion detector? So again, we have our distance in meters. So this is how close the truck is to the motion detector. And then we have time in seconds along our horizontal axis. So how far is the truck initially away from the motion detector? So initially tells us that's at time 0, and we go up, and the graph starts at 1. So we can say that in the initial distance, the truck is 1 meter from the motion detector. B, when will the truck strike the motion detector? So when the truck strikes the motion detector, that means that the distance between them is 0, obviously, because they're touching. So we just look at the graph when it reaches 0 in terms of the height, so, or the vertical component. So where does the vertical reach 0? Well, all the way over here, and that's at t equals 6. So at 6 seconds, that's when the truck will actually hit the motion detector, because there's no distance between them. They're touching. So at t equals 6 seconds. C, when is the truck not moving? So again, you have to think about the distance in meters. So if the truck is moving, remember it only moves back and forth, and this is far away, and this is super close. So the truck is not moving when the graph is just staying still. So if we look at our graph here, the graph is going up, 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 up. That means that the truck is moving. And then here, between 2 and 4 seconds, the graph just stays steady. Like the distance between the truck and the motion detector doesn't increase or decrease. So that means that the truck must be not moving here. And then after 4 seconds, the distance between the truck and the motion detector is going down. So the truck is obviously moving closer. So in this section right here, between 2 to 4 seconds is when the truck is not moving. Between 2 and 4 seconds. D, when is the truck moving away from the detector? So again, if it's moving away from the detector, then the distance will be increasing, so the graph will be going up. So the graph goes up here from 0 to 2 seconds. Then we just said that the truck's not moving between 2 and 4. And then after 4, it's decreasing. So here is what we're looking for, because the distance between the two objects is increasing during this period, so that must mean that the truck is moving away from the detector. So that's between 0 and 2 seconds. And D, when is the truck moving towards the detector? So the distance is going to be decreasing because they're getting closer and closer and closer, and that's in this period, okay, between 4 and 6 seconds. So the main idea, again, is just to use the graph, make sure you know what your variables are representing, and then try and picture it in a real-world situation. And if you have any questions, be sure to ask your instructor.